All right, we're back. We're still on page 327. We're going to knock out this second problem and see where to go from there. So find the dimensions of the rectangle of maximum area that can be inscribed in the area between the parabola y equals 9 minus x squared and the x-axis. All right, so this is actually a really common type of calculus question. Your inclination, because in geometry, it's like the answer is always a square to like every question like this. So you're probably thinking, oh, it's probably a square. It's probably not a square. But it's probably square-ish. You'll find if you do enough of these, like something square-ish about them. So let's see if we can do it. So there's one key step, and you may already know it, but we'll see as we go. So first, we need a picture. I also it's possible that you are working on notes that are spaced out differently, because even though I said I wasn't going to do it, I noticed there was like a lot of room on this page at the bottom, so I did go back and space out these notes a little differently. The real question is, did I upload them to the internet after I did that? Don't know the answer to that. So let's see. So here's 9. This will be 3. This will be -3. Okay, so parabola. You just do your best. Not bad until the end there where I totally missed. Fortunately, I didn't do it in one shot, so I can try again. Okay, that's pretty good. All right, so let's see. Let's put in a rectangle in this color. So here, then we go straight across, then we go straight down. So there's our rectangle, right? And so the rectangle can take many sizes, right? This point right here can get closer to 3, it can get closer to 0. An issue here for us, right? So we need to decide how to write the area, right? Because we're looking for the maximum area. So we want maximum area, rectangle of maximum area. And we're looking for the dimensions of that thing. So we need to write the area of this somehow. All right, so what can we do? Well, we want to do base times height, obviously, because it's a rectangle. The key to this entire problem is the point that I just put on there. How can I write that point? So we don't know what the x coordinate is. We just know that it's x. So this ordered pair is x comma, I mean, we could say it's x comma y, which would make sense. But what does y equal? Well, y is equal to this. So instead of saying xy, let's say x comma 9 minus x squared. So no matter what x is, the height of the rectangle will be 9 minus whatever x is squared. So the area of this thing, so the area as a function of x is going to be the base. But what's the base? If this distance, I don't know what color that is. I think it's this. If this distance is x, then the entire base is 2 of those by symmetry. So the base, so let's say it's base times height, but then the base is going to be 2 of whatever x is. And then the height, no matter what x is 9 minus x squared. So that's our equation. That's the only equation. We don't actually have like a helper equation in this part because we don't need it because there's only one independent variable. It's x. So we don't need another equation to get rid of another variable. We're good to go on this. One thing we do need to worry about though, what's the range of values for x? Like theoretically, and I know that it wouldn't work out, but x could be 0 and x could be 3. If x is equal to 0, then the area is 0. That's pretty clear. If x is equal to 3, the area is also 0 because when x is equal to 3, the height of the rectangle is 0. Base times height gives you 0. So at each of these, even though mathematically they're possible, you'll just get 0 for your area. So clearly they're not the answer, but they give us a closed interval on which to look, which means we can do the candidates test for this. So I think we're in good shape for this. Let's expand this just so we don't have to, it's like the product rule is fine. I'd rather use the product rule than the quotient rule, but I'd rather use the power rule more than any other rule. So when I can, I try to make that happen. So we get this, all right, a prime, 18 minus 6x squared. A prime equals 0 will give us X squared is 3, so x is plus or minus radical 3. But then remember that we have this domain restriction. So since that's the case, therefore, x is actually only radical 3. Okay, so we have one critical point, we have two endpoints, and we have an area function that's continuous. So let's say a of x is continuous. Therefore, by candidate's test, the absolute max, we only need the absolute max in this case, is an endpoint or critical point. Okay, so we can make a table, and our table is going to have x and then a of x, and our endpoints were 0 and 3, and our only critical point on the interval is radical 3. We could use the lonely critical point test on this, or theorem, lonely critical point theorem, right? If at radical 3 there's a relative maximum, it'll be the absolute maximum because it's the only critical point on the interval. So if the function changes from increasing to decreasing there, it can't change anywhere else. That must be the absolute max. But we're going to use candidate's test. So what are we testing in? We're testing in here. It's actually easier probably to use this, right? It doesn't matter. You'll get the same result out of both. 0 definitely gives me 0. 3 also gives me 0. So like you kind of know that this is going to be the maximum. So I get 2 root 3 times 9 minus 3 times 6. So 12 root 3. Okay, so therefore, so where should we, we have like a lot of room. I don't know why I'm cramming everything in here. Let me move this way down. Okay, so let's say, therefore, the absolute max is, so what are we actually finding? We're finding the dimensions. We don't actually need the area. So the absolute max is, I'm going to say it, the absolute max is 12 root 3 when dimensions are, so the x coordinate, so root 3 by, and then 9 minus root 3 squared by 6. So then how did I get 12 root 3? Oh, 2 root 3, sorry, or 2 root 3. X is root 3, but the dimensions are 2x by 9 minus x squared. So 2 root 3 by 6. Okay, so there we go. That one's not terrible at all. So the key steps here, draw a picture. Make sure you label your picture with all the things that you need. If you can come up with a closed interval, which you almost always can on these, I could have done that on the previous one also. I probably should have done that. Then you can use the candidates test where it's applicable. Sometimes it's terrible to use the candidates test though, because you need to actually be able to figure out the value of the function. And sometimes these, like the function that you're optimizing, finding the maximum or minimum of, can be like pretty terrible to plug into. So we could have used lonely critical point theorem because there was only one critical point, and we could have done a number line and seen that it was a relative max and therefore the absolute max. But we chose to use the candidates test, and like, why not? Because it was doable. All right, I'm gonna stop this here. I'll come back in the next video and we will start on the next page. So I will see you there.